Hello students, let me explain the terms, some concepts, half power points, bandwidth and Q factor. We know the average power in an LCR circuit by an AC voltage V equals to V0 sin omega t in one complete cycle is given by P equals to half V0 I0 cos phi. Here we are finding the average power over one complete cycle, that is over one time period capital T equals to 2 pi by omega. So V0 and I0 are the peak voltage and peak current. Cos phi is the power factor. Okay, this is the average power consumed in an LCR circuit over one time period. Okay, so I0 is the peak value of current is equal to V0 by Z, where Z is the impedance of the LCR circuit, which is R square, which is square root of R square plus omega L minus omega C whole square. And cos phi is again R by Z. Okay, so which is equal to Z, again we replace the same value. Now when we replace this I0 and cos phi over here, then we will get this value. Okay, V0 R into V0 square R, square root of this value and square root of this value gives you this value. Simple. Okay, now this is the power consumed in an LCR circuit. So when you put the value of omega equals to omega, when omega tends to 0 or omega tends to infinity, we get power 0. How? Because when we put omega equals to 0, then this becomes infinite. Okay, when this terms becomes infinite, then something divided by infinite is 0. Okay, when you put omega equals to 0 or omega equals to infinity, then this term would become infinite. Okay, so or something divided by infinity is again 0. Therefore both for omega tends to 0 or omega tends to infinity, the power is becoming 0. That means at very high frequency and at very low frequencies, the power delivered to the circuit is very small, or it is close to 0. So now let's check at resonance what will happen. What is resonance? As you know, at resonance the inductive reactance becomes equal to the capacitive reactance. So when omega L becomes equal to 1 by omega C, okay, we get the frequency for that as this will go to that side and becomes omega square, and this becomes LC. Therefore we get omega equals to 1 by square root of LC, and that omega, okay, this omega is a special omega because this omega is equal to omega 0, that is the resonant angular frequency. Okay, for this value of omega, which is equal to omega 0, which is called resonant angular frequency, we will get 1 by square root of LC. From this relation we get this 1 by square root of LC. So at omega equals to omega 0, that is at resonance frequency, the power becomes maximum, because at omega L equals to omega C, when this becomes equal to this terms becomes 0, and therefore the power becomes maximum, because in the denominator we have only R. Okay, therefore power becomes maximum. We get P max equals to 1 by 2 V0 square divided by R. So this is the maximum power at omega equals to omega 0. That is at resonance condition. So we can write this P max value, replace it over here. This is P max V0 square divided by 2 is P max. So we can write in terms of this, P equals to P max into this value. Now we want to show the graphical representation of power with respect to omega, with respect to the angular frequency. Here the x-axis is omega, angular frequency, and the y-axis is the power. We know at omega equals to omega 0, the power is becoming maximum. Okay, and on either side of this omega 0, the power is decreasing. Okay, and it is becoming 0 for omega tends to 0, it is becoming 0 for omega tends to infinity. So it becomes maximum at omega equals to omega 0, and on either side of this omega 0, the power is decreasing. Now we will locate the 2 points, okay, 2 points A and B, where the power becomes half of the maximum power. So we will locate the 2 points, and these 2 points are symmetrically placed. That is, they are equal distance from each other, from omega 0. They are equal distance from the omega 0. So we will get 2 points where the power is maximum, half of the maximum power. These 2 points we call it, these 2 points A and B are known as half power points. These 2 points A and B is called half power points when the power is half of the maximum power, and the corresponding frequency is called the half power frequencies. This omega 1 and omega 2 is called half power frequencies. We have another name for the omega 1 and omega 2. This omega 1 and omega 2 are also called as lower and uppercut frequencies. Okay, lower and uppercut frequencies. This all the frequencies lying between omega 1 and omega 2 are these are very useful frequencies. Okay, and the difference between this omega 2 and omega 1, which is delta omega, omega 2 minus omega 1 delta omega, represents the range of useful frequency of a resonance circuit. Okay. This omega 2 minus omega 1, which is delta omega, is the range of useful frequency for a resonance circuit. Okay, and this is popularly known as bandwidth. So we have to, this has a name which is called bandwidth. It's a range of useful frequency for resonance circuit. It also decides the selectivity of an series LC circuit that you will learn later. It also decides the selectivity of the series LC circuit. What does it mean? It means it defines how well a resonance circuit responds to a certain frequency and discriminates against all other frequencies, especially either side of omega 1 and omega 2. It is also called, it also decides the selectivity of a series LC circuit. Means there are circuits which actually allows the frequency ranging between omega 2 and omega 1, that is ranging having the value bandwidth. Okay. Therefore it is called selective. It decides the selectivity of a series LC circuit. So that's what is bandwidth. So bandwidth is the difference of upper frequency and the lower cut of frequency. It is a difference of upper cutoff and lower cutoff frequency. That is omega 2 minus omega 1 is called the bandwidth. Okay, which is the range of useful frequency of a resonance circuit, and this is known as bandwidth.